Alright, so let me begin again here. Next up, we talk about the coordinate change relation for the matrix of a linear transformation. And it is important to state that it's the matrix of a linear transformation. If you were to study coordinate change for matrices attached to other things, for example, like a quadratic form, the coordinate change property of those matrices is a little bit different. So the fact that it's the matrix of a linear transformation is important to the particular property, particular pattern of the coordinate change. So anyway, here it is. Of course, we know that we can draw this picture. I mean, we've seen this before. This is the matrix of linear transformation. And what I did in addition here was I have a basis beta and beta bar for v, dimension n, and a basis gamma bar and gamma for w, dimension m. So I can calculate the the standard matrix of this left multiplication by t beta gamma. Well, that is the t beta bar gamma bar matrix. So this is the definition of this is really that. And then if you're sneaky, you can see, wait a minute, I could rewrite that as, let's see here, I could rewrite that as phi gamma bar composed with phi gamma inverse composed with phi gamma composed with t composed with phi beta inverse composed with phi beta composed with phi beta bar inverse. And that, folks, would almost do it. You see what I did was I just put in, this is, let me underline it. So right here, this was an insertion of the identity on W, and this right here was, of course, an insertion of the identity on V, which doesn't do anything to the map, but, well, it does something to the formula, though, because then we can regroup terms, right? Use our properties about the standard matrix of a composite being the product of the standard matrices of the composed maps. And let's see here, so like, just take this, basically, and so what we get is phi gamma bar composed with phi gamma inverse, that matrix times the matrix phi gamma composed with t composed with phi beta inverse times the matrix phi beta composed with phi beta bar inverse. All right. And, well, what is this? This is nothing more than p gamma bar, that's the coordinate change matrix, times the matrix of t with respect to, I'm going to push it up just a little bit here, make sure you can see it, t beta gamma, all right, and then that is actually the inverse of the beta bar matrix. And the way to see that, of course, is that this is phi beta bar composed with phi beta inverse. So that matrix, I mean, that transformation is the inverse of this transformation, which means the matrix of this is the inverse of the matrix for that, but the matrix for that is the coordinate change from beta to beta bar. So anyway, you sort through the details here, but that right there is the coordinate change formula for an abstract linear transformation. Now I have a picture in the notes which looks a little bit different. See, I have pictured here, I thought about V being like larger dimensional and W being sort of smaller dimensional. And so that's the thing, is we don't have to have matching dimensions. Let's see here. I have, I think, an example here. Let's see. So one example is kind of a pain, but maybe worth it. What do we got? Get this page out of the way. Yeah. Get out. All right. Oh, what page was that? I guess that was page 5. Page 5. You guys probably want me to scan these, if I'm guessing. All right, so jumping over here to my example 7.56, I have this linear transformation from quadratics to complex numbers, and it's defined by basically just evaluation of the polynomial at I. So you have ai squared plus bi plus c, but of course I squared is minus 1, so that's c minus a plus ib. I introduced coordinate maps, the usual coordinate maps. Well, I mean, you got choices. In this, I put x squared first in the basis for P2 earlier in this lecture. I put 1 first, right? But anyway, so with that choice of basis, the coordinate vector of ax squared plus bx plus c is abc, and the coordinate vector of a plus ib is ab with respect to gamma 1I basis. And so if we look at it, we have the coordinate vector of the image is c minus a comma b. That follows from this formula right here, right? This is that, so that makes this the coordinate vector that, given that the basis is that, right? And so to get from there, so this is the matrix I need, right, in order to have that formula, because minus 1, 0, 1 times 0, 1, 0 times, you know, ABC. I need that to map C minus A and B for the first and second, so that makes that the matrix of T with respect to the beta gamma bases. But on the other hand, I want to look at a different set of bases, in this case x minus 2 squared, x minus 2, 1, and gamma bar. I just, to make it exciting, I flip the I and the 1. So it's a relatively benign change of base, but there it is. So I point out that you know, we can think of Taylor's theorem to understand the change of basis for the polynomials, and so I work out here that the beta bar coordinates of ax squared plus bx plus c are exactly a 4a plus b, 4a plus 2b plus c. That again comes from just re-expressing f as a polynomial centered at 2. So, you know, again, Taylor's theorem, very helpful for examples sometimes in this course. I do like that. Something I often use in my homework problems and tests. Taylor's theorem. Something you should know. Anyway, so in light of that, we find that the coordinate vector of, with respect to the beta bar basis of ax squared plus bx plus c is in fact that. All right. But on the other hand, phi beta inverse of ax squared plus bx plus c is, well, phi inverse of abc is that. So if I calculate phi beta bar composed with phi beta inverse of abc, I get this. So if I'm mapping that to that, that suggests that the matrix of phi beta bar composed with phi beta inverse is exactly, you know, 1, 0, 0, 4, 1, 0. And I mean, you can see this is why I have that there. All right. Okay, and then I say, let's work this calculation in the other direction. See, what am I doing? Oh, then I calculated the phi beta. Notice that this is opposite, the beta and beta bars are exchanged. So if I calculate the beta coordinates of a times x minus 2 squared plus bx plus c, that gives me the beta coordinates of the kind of nice vector in the beta bar basis. This has beta bar coordinates abc, right? And we work out that the beta coordinates of the this vector is just that. And again, phi beta composed with phi beta inverse would be that by the calculation above, which tells me that the coordinate change matrix in the other direction would be this. Now, if this is right, this times this should be the identity. Let's see here, that times that 1, that times that 1, that looks like, yeah, looks like we're good. So great. There's the coordinate change, both you know, both which any way you like. This is p, how'd it go? Beta bar. This is actually p beta bar beta. And the coordinate change matrix for the gamma to the gamma bar is just 0, 1, 1, 0. That's easy enough to calculate. And so if we find the matrix of T with respect to the barred basis, well, I start with the matrix with respect to unbarred basis, which I calculated at the start of this discussion, and then I multiply by the change of basis matrix for the gamma to gamma bar, and the change of matrix inverse from the beta to beta bar, which is, by the way, this, which I've already calculated. So I found it was, for this example, it was just easier to calculate this matrix directly rather than inverting that matrix, but, you know, whatever. And then there's the matrix of T with respect to the barred basis, and then just to to make a check on my calculation, I just work it out directly, right? So t of, here's my typical nice element, nice vector in terms of the barred basis, a x minus 2 squared plus. I mean, the point of this, guys, is that this vector right here, v, the matrix of, excuse me, the coordinate vector v with respect to the barred basis is just abc, right? So I work it out, and I get that. So I need this times that to give me, coordinate vector 3a minus 2b plus c and minus 4a plus b. Is that right? Oh, no, other way around, because the I comes first in the gamma bar basis. So that's got to be the first coordinate, and that's actually the second coordinates, because remember that gamma bar puts I first and 1 second. So there is a rather gory and lengthy example to explicitly flesh out the coordinate change formula for an abstract linear transformation. So I'll start again here in just a minute, because I sense the crying of babies is upon us. And in the next little bit, I will describe how to study coordinate change for linear transformations of column vectors. Thanks, guys.